thank you for the nice introduction. Thank you for welcoming me here as a keynote speaker. I have to admit, I'm a bit nervous. It's my first keynote, so please bear with me. As introduced, the talk is From Athletes to Algorithm, Transforming Canoe Technique Analysis with AI. So indeed, yes, it's a use case of AI. So briefly about me. As already introduced, my name is Marc. I'm working for TNG Technology Consulting. We're an IT service company helping various clients at difficult IT problems. I have a background in physics. I did a PhD there, but I also have a background in sports. Obviously, I'm sitting in a wheelchair. I'm born that way, so you can't ask me question whatever you like. And in parallel to my physics studies, I had a sports career where I went as a 400-meter wheelchair sprinter to 3 Paralympic Games. And with that, I also had a connection to a sports network in Germany. And there's where the talk is about. But just let me briefly introduce. TNG is not only a company which is doing IT problem solving, but they're also no, that's not where that one should go. Give me a second. That one. The innovation hacking is a department at TNG where we try out the latest, newest, hot shit. So you can have a look at the QR code there and go to the website. What you see here in the background and in this blurry video is, for example, some augmented reality stuff we try out. We have a broadcasting web show where we did deepfakes live with various people in there. So everybody became Jonas Meyer, who is the head of the innovation hacking. And we also do sometimes CEO frauds, but only with our own CEO. So this is Jonas Meyer pretending to be one of our Geschäftsführer, it's called in Germany, so CEOs. We have at aislides.com. You can have a look and get a short presentation yourself made fully with AI. Please just try it out and be ensured this talk isn't generated by AI. It's just about AI. So, what will you get today? A short introduction about where's the problem, then it split it down because the problem itself is quite complex. So as you always know, divide and conquer. You split down the overall tasks in individual splits that you then can solve. And in the end, I show the first attempt. And you probably have noticed already with AI, the first try looks really nice. And if you then try to run it in production, you figure out it's not that easy. We went through that way as well, and the lessons learned are then in the improvement and in the end in the conclusions. So, when I came to TNG after I finished my PhD in physics, I came to the innovation hacking. We thought, hey, you have a cool background in sports, and as already mentioned in the introduction, we are looking for a useful case for AI at that point. It was the 2019 around. And then I said, yeah, let's have a look. And I went to the Olympiastützpunkt in Heidelberg. That's my performance center where I trained. Went to them, asked with the current leader there, and talked about things. And then he said, we are quite strong in canoeing here. So many athletes from around Germany come to Heidelberg, train there, and prepare for the Olympic Games. And when you try to analyze their technique, what you do is you have the athletes paddling on the water, and you have a sports scientist next to the athlete taking a video of the athlete. Afterwards, bringing that file to a computer, and then going frame by frame through the video, marking the angle of the paddle toward the waterline and searching for those 4 paddle poses. When the paddle is touching the water, when it is submerged, when it is still submerged, and when it is completely immersed. Because in the textbook you find angles that are calculated to be optimal, and you want to get the athletes to that position. And yes, you have a sports scientist sitting there, clicking video frame by frame, finding those 4 paddle poses for various athletes from both sides. Takes around 20 minutes per athlete per video. And if you have 10 athletes, that poor sports scientist is a whole day doing nothing else, jump pressing an arrow button. Where I said, that's a tedious task. Can you automate that? We thought about it and said, That's an interesting challenge. Let's go for it. So what did we apply? I mean, we used computer vision at one of the examples. Not only, also AI, but computer vision, what is it? Well, it's a various topic of image processing, artificial intelligence, signal processing. It's really a big blob. That shouldn't happen. And my computer is also muted. No, today that one doesn't like me. Then I go for this presentation. So computer vision can be also, yeah, you know it from reality. If you go for the QR code that was just over there, if you have a snapshot filter, all that stuff is computer vision in application. And then going forward, how this did work? Well, in all computer vision, you have in the background a neural net. A neural net is, well, if you look at the biological version, you have somehow a cell that gets an input, and only if the input is above a certain threshold, then it fires. So you have a non-linear behavior at that point, and this is exactly what you can also then remodel in a computer. And so an artificial neural net is exactly that. You have various inputs, here in red, 3 inputs, that are weighted with various factors, combined, summed, give it a bias, and then either you reach the activation level or not. And usually you do not only have one neuron there, but you have various layers. For example, here you start on the very left with 224 times 224 pixels and 3 bits for the colors. And then you go through different layers of processing within a neural net. And in the end, you end up with 128 objects that, for example, can be detected in a neural net, mobile net in this case. And yeah, what does it do? It's a classifier. So you put in a picture of a duck, and then in the end, you get out, hopefully, that this is a duck. And as this talk is also about live demos, let me check if the gods of the live demo are today with me. Yes, they are. So let's get that bottle. Yeah, not that bad, I would say. So it can recognize the water bottle directly live on stage. The gods are with me. How do you train such a neural net? Well, as mentioned, you have these weights on the input, and then you can add some bias. And with those knobs, you can train any neural net to behave the way you want. Sometimes it's easier, sometimes it's more difficult. And in general, it's not only a few knobs, but quite some knobs, usually in the area of million, trillions, or billions. And the mathematical way is, in this case, you use reinforcement learning, that you give in pictures that are labeled, where you have the information, you apply the neural net, and you give it a loss function. So whenever it is wrong, you say, hey, that was wrong, you give it a loss, and then you try to apply a minimum loss function. So you're looking for the minimum of the loss, so you try to optimize it. That's usually the case where you can use gradient descent. That's the mathematical approach behind it, just that you have heard it. We are all low field seeker, so is a neural net, and in that way we train it. Surely the math behind is way more complex. That's just a simplification. Okay, so how can we now tackle the problem? That's also interesting that this one is there. That should be. Yes. So first, we start with finding the waterline. We narrow it down these problems to 3 things, and we narrow it down to, okay, we start with finding the waterline. And the change is quite subtle. You try to make the boat always be horizontal. And then you know, okay, the bottom part of the canoe is the waterline. And how do you find the canoe in the picture? Well, there's something called segmentation. There are neural nets out there that use or can find out which part in a picture is in the front and which one is in the back. As a human also can do that. And next live demo, let's see. Now, yes, I became a blue schlumpf. What's the English word for that one? Yeah, Smurf, thank you. Yes, I turned into a blue Smurf. I'm now here in the foreground, but I can also try to move out of the picture and just give it that one. That works not that good, but yes. So as you can see, that also works quite reliable. And if you now go for the Canoe, what you do is, okay, perfect, we know where the Canoe is. And at the bottom of the Canoe, that is our waterline. So far, so good. Now we need to figure out if we're going to the right or to the left. That you do with a principal component analysis. You're doing, you have certain features at the boat that usually stick out, like a sticker, like some ropes that are at the Canoe, stuff like that. And with the feature tracker, then you know, okay, in the next picture, the Canoe moved to the right. And with the principal component analysis, you figure out, okay, that Canoe is moving to the right. Perfect. So summary, we do a foreground-background separation. We get the main features of the Canoe. We figure out in which direction we go, and we're happy. And so far, so good. The next part is annotation. So we want to find out which angle of attack do we have. So splitting it that way. The angle of attack is, yeah, okay, somehow here, the paddle with respect to the waterline. The waterline we have found before, now we have to find the paddle. And there we make use of a well, domain knowledge, I would say. Because if you try to find paddle recognition in publicly available neural nets, that's limited. But luckily, usually the paddle is quite firmly in the hands of the athlete. And finding the hands is a lot easier because with that you can use pose detection. So, and there I didn't start the demo in advance. Pose detection, let's see. Yes. And now you see running pose detection on a laptop is not the smartest idea, but I would say it's not that bad. The pose detection can recognize my eyes, my ears, my shoulders, my arm. So far, I'm quite happy. Yes, there is a lag slightly. If I now lower the arm, yes, it takes 20 seconds. But with that one, hey, we figure out, okay, where is the athlete? And also the fan starts to spin up and my laptop takes off as expected. Luckily, I plugged in the power supply, otherwise that would have been difficult. So yes, what you do is, okay, you run your image through this open pose, and you find the eyes, you find the nose and so on. You can do that with heat maps. This is usually a step over there. And then you end up with, hey, okay, now I have the athlete knowing the position, the arm, the elbow, the wrist. And we first just ran with the wrist and figured out that's way too imprecise. That's totally off. So we needed to be more precise on finding where the angle is, because, I mean, we are looking for deviations of the angle from the textbook value that is in the order of a degree or two. And surely one of the requirements was that we don't use trackers on the paddle. So with trackers on the paddle, everybody can do that. But our task was just the athlete with the normal paddle, no additions. Okay, so what's the next step to get that more precise? And you see, that's already an AI application, and it's totally off. So yes, a lot of more domain knowledge needs to be pushed in. Well, you can use a hand detection, because when you know where the wrists are, you can narrow down the picture to just the hands, to find the hands. That's also that we learned when applying these computer vision AI use cases on stuff. Try to narrow down the information you feed into the AI. Because if you give it the whole picture, sometimes it takes a rock as a hand. No chance, yeah? But if you narrow it down and say, we know where the wrists are, and usually, as long as they're not very nasty accidents, the hands are connected to the wrist. It's enough to search around the wrist, and then the precision, accuracy, and reliability of all that algorithms become way greater. Okay, so then we find the fingers, and with the fingers we can narrow it down to the center, and here we go. That's already now following quite well the hands. And if you now apply just a straight line through it, then you get your angle. And yeah, so summary of that complex approach, combining many techniques and narrowing down the information for your algorithms to look just at the places where you are. I also could add here that we first applied a person detector just to find where the person is in order to reduce the amount of work that the neural net has to do. So you find with the neural net the pose. With the pose, you know where the wrists are. With the wrists, you know where the fingers are. Where the fingers are, you can make a center out of it. And usually in the center of the hand, you find the pedal. And with that, we have already a full running annotation using OpenPose and knowing, okay, which angle does the paddle have with respect to the waterline in every frame where the paddle is now on the right side of the athlete. On the left side, we do not see the left hand, so that's where it's limited. But on the right side, we already applied or were successful in finding the way the paddle moves. Our cool success. We're roughly 20 minutes into the talk, and you think, what am I going to talk about the next 20 minutes? That's the case where it didn't work out. So, selection. Remember, we are now here, and we need to find those 4 paddle poses. And that's just a transition. This awesomely well-made sketch is we are looking for those 4 paddle poses that you see on the left of touching the water, being submerged, still submerged, and emerge. And that's just a phase transition of being above the water, being in the water, and being below the waterline. And we are now trying to find those 4 transitions. Then I have told you now so many times it's so easy. Yeah, you take the picture of the thing you want to analyze, you run it through a neural net, and in the end you get your classification. You narrow it down, say okay. Also the technique I explained before, you narrow down the image you're looking for. We know we are going to the right, so we are looking for the right hand, and there we usually just extend the line of the canoe, and there we know there should be the paddle blade. So you take that picture, you have your model, you have your data, you get your output. With that, you're usually quite happy. Well, that's the point where it became nasty. Because, all these AI models are trained by humans. At least in most cases, you have labeled data where you put in that should it be, learn it, that you recognize it. And the market or the general interest of the public in detecting a paddle pose is limited. So we had to generate our own training data. So we got some videos and marked or extracted those areas. And then you have quite some areas. And then you have a few. And then you have working students. I'm very glad that he did that job, and he even hired afterwards at us. So obviously we didn't scare him away, but I'm really thankful for him, because that was a project that was with an extremely tight budget, and we couldn't set a consultant there and labeling those frames, and we really looked at one of our working students with puppy eyes and said, would you do that? And he said yes. And we made some tooling to make it easier. So pressing arrows for the good. Instead of the sports scientists pressing arrows to go through the video frame by frame, we made a labeler where you find, okay, we are going here, in which state are we? So Here we are in the water, here we are below the water, here we are coming again above the water, here we are above the water, and with those three arrows, we could label those quite quickly. But yes, 30,000 frames, it's not a huge number, but for one working student, he got more than one free pizza for that one. And in the end, what you do is, when you have now these labeled data, what you can do is kind of a transfer learning. You do not need to fully rewire MobileNet, but what you can do is that in the end, you just extract the endpoint. Before it was 128 different states, and we said we're not interested in these 128. We are interested just in those three. And just a short advertisement. For example, we did something similar with the DeepSeek R1 just recently, which is publicly fully open source. And I mean, if you know where DeepSeek is trained on, when you tried it out, you figure out that if you ask it certain questions, it gives you interesting answers. Those are agents that are within this neural net that are there to put rails. And as DeepSeek R1 is fully, the weights are open source, you can actually adjust those agents in order to give them proper answers also on questions, what happened on the 10-dimensional square. So this technique we applied there quite early is also possible on other publicly available large neural nets. So this use case that we did more or less for fun, it can also apply to really big LLMs now that we are using on other use cases. So quite helpful. So how good are we? Well, what you can see here is now an analysis run of the video. Every time the top left corner turns blue, we have a change in the state. So at the moment you see the paddle is recognized to be fully above the waterline. Now it comes a change penetrating, underwater, and off we go. Looks all fantastic. Well, with that, we are kind of done-ish, one could say. We find the state, well, it looks quite nice. So we have here touching the waterline. At Istwinkel is the German explanation for the current angle, and the 40 degrees is the angle it should be. And you go through those for paddle poses, and you see a proper deviation, and then you can give the athlete the feedback on how good it is. So just as a summary, what did we do? Where did we arrive? So we have the athlete paddling on the water. We have foreground-background separation, feature tracking, principal component analysis, which that we know in which direction we go. We use the open pose detection, first the person detector, to find the pose, then the hand, with the hand the center, the line. With that we go for the water line, and then we just figure out where's the paddle, try to run an analysis here, and in the end, we're done. One could think. We come to the part improvements. How good do you think that worked out, say? What do you think this approach would be? Reliably above 50%. Hands up, hands down. Reliably above 80%. Who thinks we hit 95%? Yeah, you're right. Well, it's not one-off. It's like, what are you seeing there? We had a success rate of 37%. I was like, ouch. That's like, and that's really nasty, because we first got 2 videos, and we optimized our algorithm on those 2 videos where we reached it perfect, and then we got a few other videos, and then the faces got long, really long. Was like, should we improve? And okay, I mean, I was off. We really 37%. It was a nightmare. And what we didn't take into account was another part the human brain is really good of, and the computer wasn't. First, we switched to YOLO 3 due to license reasons, and then we applied a temporal perception. Because when you look at an athlete, you know that an athlete on a video usually doesn't warp through space. It should be somehow a continuous motion. And with that, you can find outliers and also help the computer to predict the next image and find it. And that's what we actually did here. So we first improved the hand tracking and the finger tracking. And then the most important part is that one. You can see it, that we traced the center of the hand over each position and fitted it. We said that should be a curve that is differentiable, because athletes do not warp through space-time. At least I haven't seen one. And with that, okay, that's already a lot better. You then also do better feature tracking, as you know, okay, the paddle, you have usually straight lines that you can also detect quite well, so applying there. Also, human eye is, I'm using for lines in pictures, and so I find the paddle a bit better. Then we found the center of the paddle, did some fitting there again, also to smooth it. And what you see then in the end is something like this. You have a frame and the corresponding angle of the paddle with respect to the waterline. And you use a fitting algorithm, and only from the fitting you get the actual value of the paddle with respect to the waterline. Also helping then the algorithm by giving it starting point from the angle before. That helps a lot. And these before really the computer just got one image and analyzed it and gave it back without any context knowledge. And applying this context knowledge was the game changer, as it is also, for example, today in every LLM stuff. If you just ask it, give me an example of ABC without giving any context on what you expect it to be, your results will be quite off. The same here. Okay, then with filtering, we also did this strange graph where you say, how was that? That's the application of sigmoid functions, where you say, okay, what usually when the paddle is touching the waterline, and the next thing is it is submerged. It doesn't magically run up above the sky. So what you say here as the computer, if you have reached one state, then the next state is the following, and you cannot switch back and forth. That's also something we had where, for example, at the line where you are between two states, then the computer moved back and forth. And with this filtering of a sigmoid function, then you say, okay, you cannot move between those two lines, those two states. We also got new training data from the performance center. So before it was more SD quality, they invested into a HD camera. Sometimes the simple things help. If you give a computer more pixels, usually you find more details. We, as already mentioned, put in multiple images instead of single ones. We have a slightly different model, temporal filtering as is temporal perception, and we reach out in 95% accuracy on the trainings data. That was already quite impressive. We got also more trainings data. This is such a run you can see where you do a reinforcement learning. You give in the labeled data, you have your test run, and then you tune your model that way that you say, okay, which precision can you find? And we reached 95%. Okay, so conclusion, how good did we became in the end? And where are still the edges? Well, the angle of finding the angle finding, the angle detection is quite robust. That works fairly well. Also, now various detections, also quite nice. Problems occur there. That's something we haven't solved until today. We application there could have been that you say usually also the athlete doesn't move that much through the picture. But as I said, it was quite a tight budget on that one. So we thought that's probably a use case where you can just try to film the athletes while you do not have any other athletes in the background. But yeah, here you see some of the computer. As soon as the other athletes are close-ish, it thinks the other paddle I like more, and it's off. This is a fully annotated video, and well, sorry, should have shown it a bit longer. That works now, quite reliable, also at high speeds. Quite happy with that one, and now pushing for the improved numbers. So also there, when you compare to human, also human make errors. So there was also a bit back and forth on how precise do we have to get. And in the end, it was, well, off by 1 or 2 frames is actually okay. So there, also the sports scientist said, I'm also not always sure exactly which frame. And if you have 1 frame, always do your error analysis. So how much error do you get if you're off by 1 frame? Well, it's usually half a degree. Well, everybody said half a degree is okay. If the athlete is that good that you're just off by half a degree, you are fine. So also with that, requirements engineering was, as always, important also here, saying, hey, if you hit it within 1 or 2 frames, we're good. And here we went from 37 to 70% really correct and agreeing with the sports scientists. We were the next 20% was in the delta with a 1 or 2 frames off, and just 10% were really completely off. So with that, we reached 90%. And when the sports scientist said, yeah, that was a massive time saving. So now you can just drop in the analysis, you run the computer overnight, and at the next morning, you still have to look through the data, and a few data you have to correct. But overall, it's a reduction from 20 to 2 minutes per video of manual work you have to apply. And a nice other thing is, I mean, if you have already running the pipeline, you're not done with getting the pictures. You also have to write somehow, or you have to get the information to the coach. This we then also automated, that we gave them a template with LaTeX that already automatically is generated, and you have the corresponding files in the LaTeX frame. You just press compile, and then you have the PDF, and that's actually something the coach then in the end gets of the athlete. You have now the 4 paddle poses one side and the other, telling you, hey, how much off are you, where can you improve, and actually how good is the athlete, and of course for the other poses as well. And with that, we went really happy of getting 70% directly, 90% within 1 or 2 frames. We were able to compute the angular velocity at all points without any tracker, which was also something new they hadn't have before, especially for some training. They can use that to really measure, okay, how good is the angular velocity at that moment and how fast can you accelerate. You get a fully annotated video. Also, that is quite helpful for the coaches. And you get an export of all the data as a CSV file. So if the coach wants to have a look at it, they can directly apply and look through the data. And what are next steps now? Well, we could think of many cool use cases. Unfortunately, as in many sports, as soon as you move outside of the stuff that is in TV, often the funding drops. So that are just projects where we could dream of. So far, it's not possible. Technically, it is. Funding-wise, it's difficult. Real-time feedback. So with a drone, you could fly next to the athlete, have that thing lively analyzed in the cloud, and getting the feedback direct to the athlete. That is surely possible. It's complex, but the technology is there. One could do it. And Another thing is, especially with young athletes, gamification, so that you have kind of your track data. You can make a leaderboard with direct feedback. You can put in gamification, get a leaderboard here. You're that good, and provide some feedback and make, I would say, some more fun in training. That's not that unimportant. I can tell from experience. And yes, with this outlook, I would like to conclude. Thank you very much, and I'm open for questions.